Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Settle in now. Let your body become still. Let your breath move slowly and gently. There is nothing you need to solve, nothing you need to remember, only the quiet drift of thought, soft and unhurried. As we turn our attention to the vastness of the universe, the cosmos is wide beyond imagining, a silent ocean of stars scattered across unimaginable distances, yet as large as it is, as full of starlight as it seems from a distance. Most of space is darkness, cold, open, and profoundly quiet. Tonight, we will rest within that quiet and explore one of the most mysterious phenomena the universe offers, a kind of world that drifts alone, untethered, moving through darkness without a guiding sun, a rogue planet, a world without a home star, a planet exiled into the deep, moving through the interstellar medium with no sunrise, no sunset, no orbit to trace, only motion, forward, through an ocean of darkness that stretches for trillions upon trillions of miles. But before we consider the science behind such a world, before we examine its structure, its cold, its heat, its wandering path, let us simply rest in the image of a solitary planet, suspended between the stars. Imagine it now, a sphere of rock or ice, or perhaps gas and cloud, floating through the dark between star systems, so far from any source of light that its surface receives almost none, so distant from any gravitational anchor that its journey is not a circle, but a line, a drifting, unending, across the disk of the galaxy. This image is not fantasy. It is a scientific reality, a class of worlds we now believe to be far more common than once imagined. Planets set loose by gravitational encounters or born alone from collapsing clouds too small to ignite into stars. Worlds that travel in silence for billions upon billions of years. As you listen, allow yourself to settle into this scale, the scale of galaxies, the scale of slow drifting motion measured in ages rather than days, where a single journey around the Milky Way takes hundreds of millions of years, and where a lone world might complete dozens of such circuits in the lifetime of the galaxy. Let the mind soften around these distances. Let the numbers become sensations rather than calculations. Allow the immensity to steady you, to slow your inner pace, to draw you into a deeper rhythm. Because when we speak of a rogue planet, we are speaking of something that embodies quiet, a world far from the turmoil of young star systems, far from the heat of stellar radiation, far from the storms of bright atmospheres, and instead immersed in near-perfect darkness, guided only by the gentle pull of the galaxy itself. This darkness is not harsh, it is not violent or threatening, it is a natural state of equilibrium, a calm, a stillness, a kind of cosmic night that lasts for billions of years. And within that darkness, a rogue planet endures, its internal heat slowly radiating outward, its surface cooled by the faint background glow left over from the birth of the universe, its path shaped by the quiet gravity of stars it never sees. As you breathe, notice how thoughts themselves begin to drift, not with urgency, but with the same soft trajectory as a wandering planet, unhurried, unbound, floating freely across the space of the mind. When astronomers first proposed the existence of planets without stars, it seemed unlikely, almost paradoxical. How could a planet, a body defined by its orbit, exist without the star it was meant to circle? Yet as our knowledge of planetary formation deepened and our telescopes grew more sensitive, the evidence became undeniable. The universe produces planets in large numbers, far more than it produces stars, and not all of these planets remain where they formed. Many are cast out, thrown into the interstellar dark by the violence of gravitational interactions, or born alone within clouds of gas too small to ignite into fusion. The result is a hidden population of wandering worlds, invisible through ordinary means, cold, dim, and yet profoundly numerous, perhaps numbering in the trillions within our galaxy alone. Think of that now. A galaxy filled not only with stars but with planets, drifting quietly through the spaces between them. More planets than suns, more worlds in darkness than in light. Allow that idea to settle within you, like a soft weight, reassuring in its vastness, calming in its scale. Because when we look at the stars, we see only a fraction of what the cosmos holds, hidden between the lights, our countless silent worlds. As you rest here, your breath slow and steady, your body easing into stillness, imagine yourself drifting alongside one of these planets, floating beside a sphere of rock wrapped in ancient ice, or perhaps a glowing ember of a gas giant, still holding the warmth of its formation, its faint infrared glow radiating gently into the void. Around you is nothing but starlight, distant, scattered, so faint that shadows have no meaning, so delicate that the concept of day and night dissolves, leaving only constant darkness, soft and unbroken. This darkness is what a rogue planet lives within. A natural environment defined not by absence, but by equilibrium, by stability, by the gentle persistence of motion without interruption. And within this state, we begin to understand something important. The universe is not only a place of brightness and heat, it is also a place of coolness, of quiet, of deep, enduring stillness. This stillness is not empty. It is rich with meaning, rich with structure, rich with worlds that have stories to tell, stories we uncover slowly. Through careful observation, through gravity's subtle signatures, and through the soft whisper of infrared light from planets wandering alone. As you drift with these thoughts, feel the subtle shift inside, the way curiosity softens into calm, the way wonder unknots the tension of the day, the way the scale of the cosmos makes your own concerns feel lighter, not diminished but eased, spread across a wider horizon. Because when we explore these cosmic mysteries, we do not seek urgency, we do not seek drama, we seek perspective, and perspective brings rest, a spaciousness in the mind, a sense of floating, drifting, unbound by time. A rogue planet is the embodiment of this drifting, a world that has left the crowded pressures of a star system, a world that now moves through silence, its journey unhurried, its existence stretched across deep time. And so, as we open this exploration, let the image of such a world stay with you. Let it gently steady your breathing, let it guide your mind into a slower pace, a calmer rhythm, a softer awareness. You are here, listening, resting, allowing the boundaries of thought to loosen, allowing the immensity of the universe to cradle your imagination. As we begin this slow journey into the science of worlds that wander alone. Imagine again, a world drifting in darkness. To understand what such a world truly is, it helps to begin with something familiar. The simple idea of a planet, on the scale of a star system. A planet is a body that is massive enough for its own gravity to pull it into a rounded shape, not merely a jagged rock, but a sphere or near sphere. Its matter settled into balance under the inward pull of gravity and the outward resistance of its own material. It orbits a star. Held by the star's gravity in a repeating path, a closed loop carved through empty space, the period of that loop becomes what we call a year. The rotation of the planet around its own axis becomes a day. Together, these motions set the rhythm of climate, the cycle of light and dark, the sequence of seasons. In a usual star system, there is a central source of light and heat. The star fuses hydrogen into helium deep within its core, releasing energy that radiates outward through its atmosphere, across the vacuum of space, to the planets that circle it. Closer planets receive more energy. Their days are bright. Their surfaces can be hot. Farther planets receive less. Their surfaces are cool, sometimes icy, but still they are warmed, at least a little, by the constant stream of radiation from their star. This is the traditional picture of a planet, a world defined by its orbit, by its relationship to a specific star, by the way it circles, year after year, around a central source of light. Now, gently set that picture aside, and imagine something more extreme. Imagine that the planet is still there, rounded by its own gravity, massive enough to hold an atmosphere, or a shell of ice, or a deep interior ocean. But the star is gone. Not gone from the universe, but gone from the planet's life. No longer a central anchor, no longer a nearby source of light. The planet has been pulled away or thrown away from its original orbit, and now it moves on a path that does not circle any individual star. This is the essence of a rogue planet. A rogue planet is still a planet in the physical sense. It is not a star. It is not massive enough to ignite steady fusion in its core. It is not simply a small asteroid or a fragment. It is a world, with gravity, with internal structure, with a history of formation. But it is no longer gravitationally bound to a single star. Instead, it is bound to the galaxy as a whole. It orbits the common center of the Milky Way, just as stars do, tracing a slow path through the galactic disk, but on scales far larger than a single stellar system, because it has no host star. Astronomers call it a free-floating planet, or an interstellar planet, or simply a rogue. The word rogue suggests rebellion, a kind of rule-breaking, but in physics, it is less about intent and more about orbit. This is a planet whose path through space no longer corresponds to a neat, closed loop around a single sun. It travels instead on a broad curve around the center of the galaxy, passing between stars, passing through regions of greater and lesser density, moving through environments where distances between neighboring stars are measured in trillions of miles. The difference between an orbit-bound world and a starless wanderer is profound. On an ordinary planet, the star dominates the sky, daylight floods the atmosphere. The temperature of the surface is largely determined by the balance between incoming starlight and outgoing heat. On a rogue planet, there is no such balance. There is no daily sunrise, no familiar cycle of warming and cooling. The sky has no bright disk at its center, only stars, distant, sharp, cold points scattered across a black background, without a near star. The planet receives only a tiny trickle of energy from space, a faint glow from the cosmic microwave background radiation, the afterglow of the Big Bang, still present everywhere in the universe. At a temperature only a few degrees above absolute zero, left alone in this environment, a planet's surface tends to cool, radiating its heat away, ever downward, until it approaches that near-freezing background, unless something inside the planet continues to supply energy. From the outside, such a world would be incredibly faint, invisible light. It would be almost completely black, reflecting only the weak starlight that falls on it from distant suns. And there is very little starlight falling on it at all. To a telescope looking in ordinary optical wavelengths, a rogue planet is nearly invisible, a tiny dark disk against a dark background, one piece of darkness against another. Even in infrared light, where the planet's own heat might be seen, the signal is weak, a faint whisper of warmth against the cold. And yet, despite their faintness, we now think these worlds are not rare, but common. When astronomers simulate the formation and evolution of planetary systems, they find that planets interact gravitationally in complex and chaotic ways, especially in the early stages, when orbits are not yet stabilized, and when massive giants may still be migrating inward and outward. In these models, planets are often thrown into new orbits, their paths stretched, their shapes distorted. Some are flung inward, some outward, and a significant fraction are ejected entirely. Their speed carried beyond the escape velocity of the system, out into interstellar space. From this kind of modeling, and from the first hints provided by observation, now comes a surprising conclusion. There may be more rogue planets in the Milky Way than there are stars. Imagine that. For every shining sun you see in the night sky, there may be one, or several, or perhaps many more. Dark planets drifting between the stars, unlit, unseen, except in brief moments when the geometry of the universe reveals them. This population is difficult to count directly, because these planets are so faint. Instead, astronomers use indirect methods. They rely on gravity, on the way a planet's mass can briefly reveal itself by bending light. One of the key tools here is called gravitational microlensing. Picture a distant star, far beyond our solar system, its light traveling toward Earth in a straight line. Now imagine that, by chance, a rogue planet drifts between that star and our telescopes. It does not block the light like a solid disk. The alignment is usually not that precise. Instead, its gravity slightly warps the space around it, bending the path of the star's light, acting like a subtle lens. For a short time, as seen from Earth, the star appears to brighten, its light magnified by the passing planet's gravity. The effect is temporary, lasting days or weeks. Depending on the masses and relative motions involved, astronomers watch for these gentle brightenings, carefully measuring their shape, their timing, their duration. From this data, they can estimate the mass of the invisible lensing object. When the lensing mass is similar to that of a planet, and when there is no sign of an accompanying star, the simplest explanation is a rogue planet, a free-floating mass roughly comparable to a familiar world, drifting alone through space. These events are rare, because the alignment has to be exact. A planet must pass across almost the same line of sight as the distant star, and we must be watching at just the right time. But because there are so many stars in the sky, and because new surveys monitor them systematically, even rare coincidences become visible. One by one, the gravity of unseen planets reveals their presence. Another tool is infrared astronomy. Young planets and massive ones can retain significant internal heat. Long after they form, they glow faintly in infrared wavelengths, even if they are completely dark in visible light. Space telescopes that survey the sky in infrared can therefore pick out dim, cool objects that are otherwise invisible. Some of these are small failed stars, known as brown dwarfs, objects that are too small to sustain long-term hydrogen fusion, yet often massive enough to burn deuterium, a heavier form of hydrogen. For a period of time, others, lower in mass, fall into the planetary regime. They do not ignite any form of fusion, they cool steadily, their glow slowly fading over hundreds of millions or billions of years. Distinguishing between a very low-mass brown dwarf and a very massive rogue planet is not always simple. There is no sharp physical line between them, but there is a useful guideline. Above a certain mass, roughly a dozen times the mass of Jupiter, an object can briefly burn deuterium in its core. This tends to be associated with brown dwarfs, objects on the borderline between planet and star. Below that threshold, objects are more comfortably described as planets. They never ignite any fusion. They are purely gravitationally bound balls of gas or rock and ice, cooling over time. When astronomers detect an isolated object with a mass only a few times that of Jupiter, far from any star, they classify it as a likely rogue planet. If it is more massive, they may call it a brown dwarf, though there is still debate about the exact classification and about whether an object's history of formation matters more than its mass. In nearby star-forming regions, careful infrared observations have revealed solitary objects of planetary mass, too light to be stars, too isolated to be ordinary bound planets. They drift among young stars like orphans, sharing the same general environment, but not attached to any individual system. In addition to these specific cases, statistical analyses of microlensing events suggest that there must be a vast unseen population of similar worlds, too faint to detect directly, but numerous enough that their gravitational fingerprints show up in survey data. All of this leads to a picture of the galaxy that is richer and stranger than the one we grew up with. We tend to imagine the Milky Way as a collection of shining points, each point a star, many stars hosting planets, all of it embedded within a faint glow of gas and dust. Now, we must expand that picture, between the stars, within the darkness. There are likely countless planets, drifting, untethered. They do not shine, they do not announce themselves, they do not trace neat orbits that repeat over human lifetimes. Instead, they move slowly through the galactic disk, their paths influenced by passing stars, by clouds of gas, by the overall gravitational field of the galaxy. They are worlds in a state we might call planetary exile. But this exile is not an emotional state, it is a physical condition, a dynamic consequence of orbital mechanics. Gravity can be both binding and freeing. In the crowded early history of a planetary system, multiple bodies interact, energy and momentum are exchanged, some orbits contract, some expand, and some planets are given enough speed to escape entirely, to cross the invisible boundary where the pull of the star is no longer enough to bring them back. Once beyond that boundary, the planet still feels the gravity of the star, but only as one of many influences. The combined pull of all the galaxy's mass takes over, and the planet becomes a citizen of the Milky Way as a whole, not of any single sun. In that sense, planetary exile is simply the universe rearranging its matter, shifting worlds from one mode of motion to another, from the tight loops of local orbits to the broad, slow arcs of galactic travel. For a listener drifting towards sleep, there is something deeply calming in this picture. A planet can be thrown from its original home, its familiar sky taken away, its former orbit erased, and yet, its existence continues. Its structure remains. Its internal heat still flows. Its motion still follows the quiet laws of gravity. It is not destroyed, only redirected. Taken together, the classical idea of a planet, the transformation into a free-floating world, the faintness, the cold, the immense distances, the difficulty of detection, the subtle tools of microlensing and infrared surveys, the distinction between massive planets and small failed stars. All of these pieces give us a scientifically grounded picture, a galaxy filled not just with luminous systems, but with a hidden architecture of dark worlds, moving through space on timescales beyond our lives, beyond our civilizations, beyond even the lifetimes of many stars. As you rest with this knowledge, you can let your thoughts become like those worlds, unhurried, drifting, unbound by immediate concerns, carried gently by the gravity of curiosity, through a universe that is deeper and quieter than it appears at first glance. In the quiet we have created together, let your mind drift back in time, not just years or centuries, but all the way to the earliest stages of a planetary system's life. Every planet, rogue or not, begins as part of a larger structure, around a newborn star. There is usually a disk of gas and dust. We call it a protoplanetary disk, a flattened whirl of material, rotating around the star much as the rings of Saturn circle that planet, but on a far greater scale. Within this disk, tiny grains of dust collide. They stick together through electrostatic forces, forming clumps, then pebbles, then larger bodies. Step by step, matter organizes itself, guided by gravity and by the motion of the disk. Over time, some of these clumps grow large enough that their own gravity becomes important. They attract more material, sweeping up dust and smaller rocks as they move through the disk. These growing bodies are called planetesimals, the seeds of future planets. In some regions, especially beyond the point where water and other volatiles freeze, these seeds can grow rapidly. They accumulate thick shells of ice and rock, and if they reach enough mass before the disk dissipates, they can begin to pull in gas directly, forming giant planets with deep atmospheres, rich in hydrogen and helium. All of this, from dust to planets, unfolds in only a few million years, a short time compared with the life of a star, but long enough for intricate gravitational dramas to play out. The early solar system is not a tranquil clockwork. It is a crowded, dynamic environment. Multiple forming planets tug on each other. They exchange angular momentum. They shift their orbits inward and outward. Massive giants in particular can migrate. Interactions with the surrounding disk cause them to spiral closer to the star or farther away, depending on how they exchange angular momentum with the gas. When several giant planets are present, their mutual gravity can lead to close encounters. Orbits can become elongated. Inclinations can change. The architecture of the system can rearrange itself repeatedly. In this gravitational dance, not all planets find stable places to remain. This is where the story of exile begins. Consider a young planetary system, a star at the center, a handful of giant planets forming beyond the line where water freezes, and several smaller rocky planets closer in. At first, their orbits may be relatively smooth, but small imbalances, tiny differences in their initial positions, can grow over time. Two giant planets might draw nearer in their orbits. They might pass each other at relatively close range. On astronomical scales, close can still mean tens of millions of miles. Yet the gravitational effect of such an encounter can be profound. A close encounter between massive planets is like a slingshot. One planet can steal orbital energy from the other, leaving one on a tighter, more circular path, while the other is flung outward, placed on a more elongated orbit. If these encounters repeat, or if several planets are involved at once, one of them may gain enough energy to exceed the escape velocity of the system. At that point, its path is no longer a closed loop around the star. It becomes unbound. Its orbit opens into a long curve that leads it out into interstellar space. It has become a rogue planet. This process is called planet-planet scattering, and simulations of young planetary systems show that it is common, especially when there are several giant planets of comparable mass, competing for stable orbits. Smaller planets, such as terrestrial worlds similar in size to Earth, can also be affected. They may be perturbed by the giants, their orbits stretched into long ellipses, their paths crossing those of larger bodies, leading to further gravitational encounters. Because smaller planets have less mass, they are easier to accelerate. Their velocities can be changed more dramatically by encounters with large neighbors. This makes them easier to eject. Their gravitational grip on the system is weaker, so a single close approach to a giant may be enough to send them out. In extreme cases, even a planet similar to our own could have been flung into space, if the early architecture of the solar system had been only slightly different. Interactions with Jupiter or Saturn could have placed Earth on an unstable orbit, one that eventually escaped the sun's pull. In our particular history, that did not happen. Our planet found a stable path, but there is nothing in the laws of physics that guarantees such stability for every world. The outcome depends sensitively on initial conditions, on how many planets formed, on how massive they were, on how the surrounding disk evolved. In addition to internal gravitational chaos, there are external influences. Stars rarely form in complete isolation. They are often born in clusters, groups of many young suns emerging from the same giant molecular cloud. In such a cluster, stars pass relatively near one another in their early lives, not close enough to collide, but sometimes close enough for their gravity to tug at each other's planetary systems. A passing star can distort the outer orbits of planets and comets, especially if those planets lie far from their host star. Beyond the region of strong gravitational binding, an outer giant planet that once orbited serenely can have its path stretched, its orbit tilted, or its direction altered. In some cases, the influence of a stellar encounter can amplify the chaos already present within the system, triggering a chain reaction of scattering events, and increasing the likelihood that one or more planets will be ejected entirely. These processes do not occur over days or years. They unfold across millions of years. The system evolves slowly, orbits shift gradually, repeated encounters accumulate. Eventually, one planet crosses a threshold. Its path is altered just enough, and gravity does the rest. The moment when a planet becomes unbound is not marked by a sudden explosion. There is no visible sign, no shock wave or flare. It is simply the point at which its trajectory ceases to loop back toward the star. The point at which, mathematically, its total energy with respect to the star becomes positive, and from then on it will drift away, its distance increasing without limit. In practical terms, the planet may continue to pass through the outer fringes of its former system for some time, crossing large orbits, passing through regions filled with comets and debris. But each pass carries it farther outward. Each loop is more open than the last, until eventually the star's gravity is just one influence among many, and the planet has joined the slow circulation of matter around the galaxy itself. Simulations that follow large numbers of young planetary systems show that ejection is a normal outcome, not a rare anomaly. When researchers start with disks containing many forming planets, they often find that a significant fraction of those planets do not remain in stable orbits. Instead, they are scattered inward to be consumed by the star, or outward to become rogues. These computational experiments are like watching a speeded-up history. Millions of years compressed into minutes of model time. Orbits that begin nearly circular become stretched and twisted. Planets cross paths. Close encounters switch their positions. Some are thrown so far out that the star can no longer hold them. The final planetary system, after all of this gravitational sculpting, may contain only a handful of survivors. The stable arrangement we see in a mature system may be the end result of extensive pruning, with many worlds lost to interstellar space. But not all rogue planets begin as exiles. Some may form directly in isolation, in regions where stars are born. The gas of a molecular cloud does not fragment into identical pieces. Some clumps are massive enough to form stars that ignite hydrogen fusion. Others are smaller. They may collapse under their own gravity, but never reach the central temperatures and pressures required to sustain fusion. If such a collapsing fragment has a mass comparable to that of a giant planet, it may become a free-floating object from the very beginning, never orbiting a specific star. Instead, it forms directly as a solitary body, a kind of starless planet. Whether we call such an object a planet or a brown dwarf depends partly on its mass and partly on how we choose to define the word planet. Some classification schemes emphasize formation history, arguing that planets should form within disks around stars, while others focus more on mass and internal physics. From the perspective of a listener drifting towards sleep, the exact label matters less than the physical reality. There are objects in space, with masses similar to those of planets, that do not orbit stars. Some are born that way. Others are thrown out of their original systems. All of them move in long, slow arcs through the galaxy. Once a planet is ejected, its speed relative to the star it left is typically a few kilometers per second, a few thousand meters each second. On human scales, this is extremely fast. On galactic scales, it is modest. Such a planet would take tens of thousands of years just to move a single light year. It would require millions of years to travel from one typical star system to another, and hundreds of millions of years to complete a single orbit around the center of the Milky Way. Over 1 billion years, a rogue planet could traverse large regions of the galactic disk, passing within distant view of many stars, perhaps moving through the outskirts of clusters, skirting the edges of giant molecular clouds, always pulled but never captured, unless a rare and precise gravitational configuration brings it into a new bound orbit. Ejection therefore changes not only the planet's local environment, but also the timescale of its story. It is no longer living on the schedule of a star's day and year. It inhabits the slower, broader timescale of the galaxy itself. The chaotic early epochs of planetary evolution, the gravitational instability inside protoplanetary disks, the scattering between planets, the close encounters with migrating giants, the occasional influence of passing stars, the simulations that reveal whole systems unraveling, and the possibility of planets forming directly from collapsing clouds without stars. Altogether, these processes make rogue planets an expected and natural outcome of cosmic evolution. Not an odd exception, but a common thread in the fabric of planetary formation. As you contemplate this, you may sense a kind of paradoxical calm in the chaos. On short timescales, the early lives of planetary systems are turbulent. Orbits shift, planets collide or are flung out, configurations change, but on longer timescales, structures emerge, stable planetary systems settle into place, and the ejected worlds find their own trajectories, not destroyed. But given a different role in the architecture of the galaxy, you can let this pattern echo gently inward, moments of turbulence, followed by long arcs of stability, short episodes of rearrangement, followed by quiet, by drift, by enduring motion through a larger, more spacious context. Worlds are born in crowded disks. Some remain, some are exiled, yet all obey the same underlying laws. All follow paths determined by gravity, by mass, by energy. In this sense, even exile is a form of order, a different solution to the same equations, a different way of being a planet in a galaxy filled with stars. As your breathing remains slow and steady, you can imagine these processes not as sudden violence, but as an immense, slow choreography, played out over millions of years, where every ejection, every scattering, every shifted orbit is part of the universe settling into a configuration that can endure. The young system is noisy. Then it quiets. The planets that remain in orbit trace their loops for billions of years. The planets that were cast out drift away into the dark, becoming the rogue worlds that wander between the stars, and somewhere, perhaps many light years from any sun, one of those worlds travels on, bearing within it the memory of its violent birth, but now moving through a medium of silence, a planet in exile, yet fully at home in the wider gravity of the galaxy. Between the stars, there is a kind of space that is easy to overlook, a medium so thin, so quiet, that at first glance it seems like nothing at all. Yet this is the environment that a rogue planet must cross, for millions and billions of years. To imagine the life of such a world, we have to slow down and picture not just the planet itself, but the ocean of near emptiness it moves through. When we think of space, we often picture a perfect vacuum, a place without air, without matter, without anything at all. But real interstellar space is not perfectly empty. It is almost empty, which is very different. Between the stars of our galaxy, there are atoms and ions, single particles of hydrogen and helium. There are tiny grains of dust, complex molecules, regions where gas is slightly denser, and regions where it is thinner. There are large clouds of cold molecular gas, and hot, diffuse bubbles carved by stellar winds and ancient supernova explosions. This mixture is called the interstellar medium. On average, In a typical region of the Milky Way's disk, there may be only a few atoms in each cubic centimeter of space. A cubic centimeter is the size of a sugar cube, a volume small enough to sit on your fingertip. Here on Earth, at sea level, there are roughly 10 billion trillion molecules of air in that same volume. So the interstellar medium is extremely rarefied, far emptier than even the best laboratory vacuum humans can create. For a rogue planet, this means that the surrounding space does not press on it in any noticeable way. Its motion is not slowed by drag. It does not feel the kind of resistance that an object experiences moving through air or water. It coasts, almost perfectly. Under the influence of gravity alone, the temperature of this medium varies. In some regions, the gas is warm, thousands of degrees, heated by starlight and shocks from stellar winds. In other regions, it is cold, just a few tens of degrees above absolute zero, shielded from radiation and cooled by the expansion of the universe. Yet because the gas is so thin, temperature in this context does not feel like temperature at a planetary surface. Even if individual atoms move rapidly, there are so few of them that they carry almost no heat. From the perspective of a planet's surface, the more important influence is not the temperature of the gas, but the cosmic background radiation that fills the universe. Everywhere in space, there is a faint bath of microwave light, the afterglow of the Big Bang. This radiation corresponds to a temperature of just under 3 degrees above absolute zero. It sets a kind of minimum temperature for any object left in space for long periods. If a world were completely isolated, and if it produced no heat of its own, its surface would gradually cool until it was only a few degrees above absolute zero, very close to that cosmic background temperature. A rogue planet, drifting far from any star, is immersed in this background, plus the very faint visible and ultraviolet light from distant stars, and occasional higher energy particles from cosmic rays, but the net external heating is very small. As a result, the outermost layers of such a world tend to become extremely cold. If the planet has an atmosphere, it may condense and freeze, forming thick layers of ice or exotic snow on the surface. If it lacks a substantial atmosphere, its bare rock or ice will radiate away heat into space, cooling slowly toward equilibrium with the background. In this deep cold, day and night lose their usual meaning. On a world that orbits a star, night is the period when the planet's rotation turns a given location away from the star. Darkness is temporary, followed reliably by dawn. On a rogue planet, there is no central star in the sky, no disk of light to rise or set. The sky is always dark, lined with stars that are distant and unchanging. The only variations in light might come from the galaxy itself. If the planet passes through regions where the Milky Way's starlight is denser, or through the outskirts of a nebula, the sky might show subtle hazes or bands of brightness, but these changes would be slow, evolving over tens of thousands or millions of years. For any being on the surface, if the surface were accessible, night would be effectively eternal. This eternal night is not an absolute absence of light. Starlight still falls on the planet from all directions, but each star is only a tiny contributor. Even the brightest star in the sky, other than the one the planet left behind, would be no more than a point, too faint to cast strong shadows, too distant to warm the surface in any significant way. When we ask, what does a rogue planet feel as it moves through this environment? We must remember that a planet itself has no nerves, no sensations, but its physical state can be described. It feels almost no pressure from outside. The interstellar medium is too thin to exert more than a negligible force. Its path is unmuffled by air resistance, so it maintains its velocity nearly unchanged. Only the gravity of stars, dark matter, and the broad potential of the galactic disk gently curve its motion. The gravitational pull from the galaxy acts like an invisible track, guiding the planet along a huge orbit around the galactic center. This orbit may be nearly circular or slightly elongated, depending on the planet's initial speed and position, but the curvature is gentle, spread over tens of thousands of light years. Compared with the tight loops of planetary orbits around a star, this galactic orbit is vast and slow. As the planet travels, it may cross different phases of the interstellar medium. It might move through a relatively empty region, where the gas density is extremely low, then gradually enter a slightly denser area, perhaps the outer part of a diffuse cloud. in the densest molecular clouds, where stars themselves are born. The gas and dust can become much more concentrated, thick enough to strongly absorb and scatter starlight. From inside such a cloud, the visible sky would grow even darker, while infrared radiation from the cold dust might become more prominent. For the planet, passing through such a cloud could have subtle effects. Its outer atmosphere, if it retains one, might interact more strongly with the gas. It might collect additional material, or experience weak drag over very long timescales. But these changes happen slowly, spread across millions of years, so the planet's journey remains smooth and continuous. There is another component of this environment, invisible, yet dynamically important. Dark matter, in and around the Milky Way. There is believed to be a large amount of matter that does not emit or absorb light. We infer its presence from its gravitational effects, on the rotation of the galaxy, on the motions of stars, and on the bending of light from distant objects. A rogue planet moving through the galaxy feels the combined gravitational pull of the visible matter, stars, gas, dust, and the dark matter halo that surrounds them. This dark matter does not interact with the planet in any other known way. It does not collide with its atoms. It does not slow it down. It only contributes to the overall gravitational potential. In a mathematical sense, the planet moves through a landscape shaped by both visible and invisible mass. Its trajectory is a response to that landscape, a slow, graceful curve adjusted by each passing star, each cloud, each region of denser or thinner dark matter. From a human perspective, we often focus on brief events, moments when something happens quickly, but for a rogue planet, nearly everything is slow. The time required for such a world to cross from one spiral arm of the galaxy to another can be on the order of hundreds of millions of years. During that time, stars are born and die. Entire civilizations could rise and fall many times over, while the planet continues its silent drift, almost unchanged. This extreme slowness contributes to the feeling of isolation. Think about distance. The nearest star to our sun is roughly 4 light-years away. Light, which travels at about 300,000 kilometers per second, takes 4 years to cross that gap. A rogue planet passing through the typical interstellar neighborhood might move at tens of kilometers per second relative to the stars around it. That sounds fast, but compared with the speed of light, it is tiny. At such speeds, it would take tens of thousands of years just to traverse a single light year. To move from one typical star system to another could take hundreds of thousands of years, or more. So even if a rogue planet's path carries it relatively near other stars, those encounters are rare on human timescales. The intervals between them stretch across immensities of time, making each close passage a brief, almost negligible episode in the planet's overall story. For most of its journey, the planet will be surrounded by emptiness, with other stars always far away. This is what we mean when we say that such worlds are truly isolated, not because the galaxy lacks structure, not because there are no stars at all, but because the distances and timescales are so vast that, from the point of view of any surface or subsurface environment on the planet, the external universe changes almost not at all over the span of many generations, or even entire species' lifetimes. If life were somehow present, in this way, the physical environment of deep interstellar space provides a stable, nearly unchanging backdrop, cold, dark, quiet. Against this backdrop, the most important source of energy for a rogue planet is usually not the outside, but the inside. Internal heat dominates, generated by radioactive decay of long-lived elements within the mantle and core, by residual heat from the planet's formation, or by more exotic processes if it has an unusual history. This internal heat flows outward, trying to escape into space, but the rate at which it escapes is moderated by the planet's composition, by the thickness of its crust, by any atmosphere or ice shells, by the details of its geology. Because the external environment is so cold, the temperature difference between interior and space can be very large. This drives a steady outward flow of energy, but also allows layers within the planet to remain relatively warm compared with the surface for very long periods of time. Meanwhile, the interstellar medium around the planet changes slowly. The density of gas may fluctuate. Cosmic rays may occasionally inject bursts of high-energy particles. The The background starlight may gradually brighten or dim as the planet moves closer to or farther from dense regions of the galactic disk, but these changes are gentle, spread across timescales that are hard to grasp. In some parts of its orbit, the rogue planet might pass slightly above or below the main plane of the Milky Way. In those regions, the density of stars is lower, the sky would appear somewhat thinner, the band of the galaxy across the sky narrower. In other regions, it might re-enter the denser midplane, where the Milky Way shines as a thick, luminous band. Yet even this change, from a fuller star field to a sparser one, would unfold slowly, on timescales that dwarf human history. All of this contributes to an almost meditative stability. The external environment does not shock the planet. It does not bombard it with abrupt transitions. It simply surrounds it with a persistent, cold, low-density medium, within which the planet's own internal processes can play out. If we step back and think of the galaxy not as a flat picture, but as a dynamic system, we can see rogue planets as small, dense parcels of matter, moving through a vast, dilute sea of gas, dust, stars, and dark matter. Their journeys are influenced by gravitational interactions with this environment, but only gently. Most of the time, they move through regions where the nearest star is many light years away, where even a large molecular cloud might be a distant, faint silhouette. In that sense, the environment of deep interstellar space is both simple and subtle. Simple, because its average properties can be described with a few numbers: a gas density of a few atoms per cubic centimeter, a background radiation temperature of just under 3 degrees above absolute zero, an almost complete absence of external pressure. Subtle, because small variations in density and gravitational potential, integrated over millions of years, can slowly alter the planet's course, tilting its orbit, shifting its position within the galactic disk, carrying it from one large-scale environment to another. From the vantage point of someone drifting into sleep, you can think of this as a kind of cosmic stillness with a slow, barely noticeable current. The rogue planet is a dense, solid object, moving through an almost intangible medium, its internal life shaped by its core and mantle, its external life shaped by gravity and time. When you imagine such a world, you can picture it gliding through darkness, surrounded by the faint glow of the distant Milky Way, its surface cold, its interior quietly warm, its path guided by forces that act gently but persistently, across spans of time longer than the history of life on Earth. The night around it never ends. Yet that night is not hostile. It is simply the natural state of most of the universe, a state in which a planet can drift. For as long as the galaxy itself endures, as you rest with that image, you may feel a parallel inside yourself, a sense of drifting within a larger quiet, supported by an environment that is steady, vast, and unhurried. The planet continues its journey through deep interstellar space, across regions of different density, within the combined gravity of stars and dark matter, under an eternal, cold, gentle night. And within that unending night, its own internal story unfolds, guided by the heat, chemistry, and structure locked inside. Deep inside any planet, far below the surface, there is a quiet struggle between heat and cold. Heat flows outward, always, seeking the cold of space, while the universe beyond remains at only a few degrees above absolute zero, a stable, unforgiving sink for energy. For a world that orbits a star, starlight complicates the picture. Energy pours in from outside, surfaces are warmed, atmospheres circulate, the balance between incoming and outgoing energy shapes climate. For a rogue planet, the outside is almost entirely cold, the star is gone, external heating becomes negligible, and the story of temperature is written mostly from the inside outward. The first source of internal heat lies in the planet's birth. When a planet forms, material falls inward under gravity, dust and gas collide, fragments merge, kinetic energy is converted into heat. This accretional heat can be intense in the early stages, especially for large planets. Their interiors may become partially or fully molten. With oceans of magma deep beneath a forming crust, over time, this primordial heat leaks away. It escapes through convection in the mantle, through volcanic eruptions, through conduction across the crust, and finally through radiation into space. But the process is slow, especially for large planets. Big planets have more volume than surface area, meaning they can store more heat compared with the rate at which they lose it. A massive rogue planet, perhaps similar in mass to Jupiter, or several times more massive than Earth, can hold on to a significant amount of this initial warmth for billions of years. Even as its surface cools toward the temperature of the cosmic background, its deep interior can remain warm, or even hot, for a very long time. The second important source of internal heat comes from the decay of radioactive elements. Within the rocks of a planet's mantle and crust, there are isotopes such as uranium, thorium, and potassium-40. These isotopes are unstable on long timescales. They undergo radioactive decay, transforming into other elements and releasing energy in the process. This energy appears as heat, tiny amounts in any given moment, but integrated across the huge mass of a planet, it becomes significant. On Earth, radioactive decay still provides a substantial fraction of our internal heat today. Billions of years after the planet formed, it helps drive mantle convection, plate tectonics, and volcanic activity. A rogue planet with a similar composition would also carry this internal power source. Whether or not it has a star, even if accretional heat gradually fades, radioactive decay continues, providing a slow, persistent trickle of energy from within, like embers buried deep inside a thick blanket of rock. A third source may have contributed earlier in the planet's history, even if it is no longer active after ejection. Before leaving its home system, a planet may have experienced intense tidal heating. Tidal heating occurs when a planet orbits close to a massive body, and its orbit is not perfectly circular. As it moves closer, gravitational forces stretch it. As it moves farther away, those forces relax. This repeated stretching and relaxing flexes the interior, generating friction and heat. We see a strong example of this in Jupiter's moon Io. Io is heated so strongly by tidal forces from Jupiter and other moons that it becomes the most volcanically active body in the solar system. Its surface is constantly reshaped by eruptions. Other moons, such as Europa and Enceladus, experience gentler tidal heating, enough to maintain subsurface oceans beneath thick ice shells. Despite receiving little sunlight, if a planet were once in a tightly interacting configuration with a massive neighbor or close to its star, it might have been heated tidally over long periods. That energy would have contributed to its internal temperature, perhaps partially melting its interior, driving vigorous convection, and establishing a complex thermal history. Once ejected, tidal forces from the original star and neighboring bodies would diminish, so this particular source of heating would fade. But the thermal state created by that history would remain. Heat stored in the interior would continue to leak out slowly, joining the energy provided by radioactive decay. All of these heat sources work together: accretional leftovers, long-lived radioactive elements, past or present tidal interactions. They create a warm interior surrounded by a cold universe. The question then becomes, how does this heat travel from the deep interior to the surface? Inside a rocky planet, heat moves primarily by conduction and convection. In conduction, energy passes from atom to atom, from warmer regions to cooler ones, like heat moving along a metal rod from one end to another. In convection, material itself moves. Warm, buoyant rock slowly rises. Cooler, denser material sinks. This creates large-scale circulation patterns within the mantle, similar in principle to the way warm air rises and cool air sinks in an atmosphere, but on much longer timescales and in solid rock that behaves like a very viscous fluid. Convection is efficient at transporting heat. A convecting mantle can move energy from the core toward the surface more quickly than conduction alone, though quickly in this context still means millions of years. At the surface, the heat must cross the crust, the outermost solid shell. If the crust is thin and fractured, heat can escape more easily. If it is thick and rigid, it can act as an insulating layer, slowing the loss of energy into space. Volcanic activity, if present, can puncture the crust, bringing hot material to the surface and releasing gases into any surrounding atmosphere. This provides localized pathways for heat to escape, but it also reshapes the surface, potentially refreshing it with new materials and altering the chemistry of any surface or subsurface environments. Now we add another layer to this picture, the atmosphere. If a rogue planet manages to retain a thick atmosphere, its internal heat can be trapped more effectively. This is where the physics of the greenhouse effect becomes crucial. On Earth, The greenhouse effect arises because our atmosphere allows visible light from the sun to reach the surface, where it is absorbed and re-emitted as infrared radiation. Greenhouse gases such as carbon dioxide and water vapor absorb some of this infrared radiation and re-emit it, slowing the escape of heat into space. This keeps the surface warmer than it would be without an atmosphere. On a rogue planet, there is almost no incoming visible light from a nearby star. Yet the greenhouse effect can still operate because the interior continues to supply heat. That heat travels outward and reaches the base of the atmosphere, where it is radiated in infrared wavelengths. If the atmosphere contains molecules that absorb infrared radiation efficiently, they can trap some of this energy and re-emit it in all directions, including back toward the surface. This reduces the net rate at which heat escapes into space, allowing the planet to remain warmer than it otherwise would be. Despite the lack of starlight, hydrogen, the lightest and most abundant element in the universe, plays a special role in this scenario. At high pressures, thick hydrogen atmospheres can be surprisingly good at trapping heat. A rogue planet with a mass several times that of Earth could potentially hold onto a deep envelope of hydrogen and helium acquired from the original protoplanetary disk. If that envelope is not stripped away before ejection, it can act like a powerful insulation blanket. Models of such worlds suggest that, with a sufficiently thick hydrogen atmosphere, a planet could maintain surface temperatures near or even above the freezing point of water. Even without any starlight, the combination of internal heat and strong atmospheric insulation would be enough. In this case, the outer layers of the atmosphere would be extremely cold, chilled by the cosmic background, while deeper levels, closer to the warm surface, would be much hotter, creating a strong temperature gradient. Yet from the perspective of a lake or ocean at the base of such an atmosphere, conditions might be surprisingly temperate. Even if the planet does not preserve a thick hydrogen envelope, there are other possibilities. Consider a rocky world roughly the size of Earth, ejected from its system after forming oceans, atmosphere, and a working geology. Once in interstellar space, the lack of starlight would cause its surface to cool. Water at the surface would freeze, forming thick ice layers. Over time, the atmosphere itself could partially or fully condense and become trapped within the ice. The surface would become a frozen shell. Yet beneath that shell, all the processes we have discussed would continue. Radioactive decay would still generate heat. Residual warmth from formation would still leak outward, possibly joined by heat from any early tidal interactions it once experienced. If the rate of internal heating is high enough, and if the ice layer is thick enough to act as an insulator, then at some depth beneath the frozen surface, the temperatures could rise above the melting point of water. There, a subsurface ocean could form, a global layer of liquid water sandwiched between ice above and rock below. We see analogs of this in our own solar system. Jupiter's moon Europa appears to have a deep ocean beneath an ice crust. Its internal heat is supplied mainly by tidal flexing due to Jupiter's gravity. Saturn's moon Enceladus also likely houses a subsurface ocean, with geysers at its south pole venting water vapor and ice grains into space. Even far from the sun, at the cold outer edges of the solar system, these internal oceans remain liquid because of heat generated inside the moons and trapped by insulating layers. On Earth, we can look to subglacial lakes in Antarctica for another analogy. There, thick ice sheets insulate liquid water below. Despite the frigid surface climate, heat from the interior of Earth, combined with pressure and insulation, keeps these hidden lakes from freezing solid. A rogue planet could be similar on a global scale, its entire surface frozen, but beneath the ice, an ocean circulating slowly, resting directly above warm rock and occasionally interacting with hydrothermal vents. In such a world, the surface might be unimaginably cold, but the interior ocean could maintain moderate, stable temperatures for billions of years, as long as internal heating and insulation remain in balance. The timescales involved are enormous. Radioactive isotopes such as uranium-238 and thorium-232 have half-lives of billions of years. They decay slowly, providing a persistent source of heat over much of the age of the universe. As long as the planet retains enough of these elements, and as long as its structure allows that heat to be transported outward, Liquid layers can persist, even in absolute darkness. Because of this, models of rogue planets suggest that habitable conditions, defined in the minimal sense as the presence of stable liquid water and energy gradients, could last much longer than the lifetimes of many stars. The energy flow from inside to outside also gives such worlds a unique observational signature. Even if a rogue planet is completely black in visible light, it will still emit infrared radiation according to its temperature. If it retains enough internal heat, its average temperature may be far above the cosmic background, perhaps tens or hundreds of degrees above absolute zero. This difference causes it to glow faintly at longer wavelengths. Infrared telescopes in space, sensitive to these wavelengths, can in principle detect such objects, especially the more massive and younger ones that have not yet cooled very far. We have already found isolated objects of planetary mass this way, some in nearby star-forming regions, others scattered through the galaxy, their faint infrared glow marking them as warm bodies in a cold universe. For an individual rogue planet, the details of its internal heat budget will depend on many factors. Its mass. More massive planets store more heat and lose it more slowly. Their surface gravity also helps them retain thick atmospheres that can enhance insulation. Its composition. Richer concentrations of radioactive isotopes lead to higher internal heat production. More volatiles such as water and carbon compounds influence what phases of matter exist at different depths. Its history. A world that experienced strong tidal heating early on might have undergone widespread melting, creating layered structures, differentiated cores, and long-lasting thermal gradients. Its outer layers, a deep hydrogen atmosphere, a water ice shell, a rocky crust, each configures the rate at which heat escapes and the potential for liquid layers to exist. Despite the complexity, a common thread emerges. Rogue planets are not just cold rocks drifting through space. They are thermal systems, with interiors that evolve slowly, powered by deep time processes, insulated from the cosmic cold by their own structure. From the perspective of someone listening in the dark, letting their thoughts drift into sleep, there is something deeply calming about this. Even in the coldest reaches of interstellar space, a planet can carry its own warmth, shielded by ice or atmosphere, its energy flowing outward at a measured pace, unaffected by the sudden changes that dominate our daily lives. The universe around it remains nearly constant, a background at just under 3 degrees above absolute zero. But inside, there are layers of rock, metal, ice, and possibly liquid, all shaped by the slow physics of heat and gravity. You can imagine such a world now, its surface locked in perpetual night, frozen plains stretching for thousands of kilometers, cracks in the ice occasionally shifting as the interior moves. Beneath that shell, a dark ocean quietly circulating, heated from below by a rocky mantle that is still warm, still slowly cooling, billions of years after the planet formed, far deeper. At the core, radioactive isotopes continue to decay, adding their small but steady contribution, ensuring that the interior does not freeze completely, maintaining gradients that allow energy to flow from center to surface, from past to present, from inside to outside, and above it all, the interstellar medium remains cold and thin, ready to accept whatever heat the planet releases, yet never overwhelming it, never intruding. In this way, a rogue planet is like an ember drifting through a vast, dark room, its glow invisible to our eyes but very real in the infrared. A self-contained island of heat, traveling through an ocean of cold. As you rest with this image, you can let your own sense of warmth feel similarly self-contained, your body generating heat from within, surrounded by a cooler room, by a larger world, by a universe that is mostly empty, yet gently supportive. The planet continues to drift, its internal heat flowing outward, its outer layers in contact with deep space, its hidden structures evolving at a pace so slow that entire civilizations would rise and fall before anything noticeable changed at the surface. Quiet, enduring. In the darkness between the stars, where no dawn ever comes, it is natural to wonder, could anything live there? If a world has no sun, no daily flood of light, no familiar rhythm of day and night, is life impossible, or simply different? On Earth, life as we see it every day is tied to sunlight. Plants and algae capture light using photosynthesis. They convert photons into chemical energy, building sugars from carbon dioxide and water. These sugars then support almost all larger food webs. Animals eat plants, or eat other animals that ate plants. And so the energy that began as sunlight flows through the entire biosphere. It is easy to generalize from this, to assume that life anywhere must begin with light, that a star is required, that without a sun, there can be no biology. But Earth also contains a quieter, darker example, deep beneath the ocean surface, in regions where sunlight never reaches. Near cracks in the seafloor where hot water bursts out, there are ecosystems that do not rely on light at all. At these hydrothermal vents, water heated by the planet's interior rises through the crust, carrying dissolved minerals, including reduced forms of sulfur and other elements. When that hot water mixes with the cold, oxygen-rich seawater above, steep chemical gradients appear. Microorganisms there do not harvest light, they harvest chemistry. They perform chemosynthesis, using chemical reactions between reduced and oxidized compounds to power their metabolism. They build organic molecules from inorganic ingredients, without ever seeing the sun. Around these microbes, complex communities grow: tube worms, clams, crustaceans, entire food webs supported by the flow of chemical energy from the interior of the Earth. Rather than by light from the sky, this shows us something crucial. Life does not fundamentally require light, it requires free energy, a way to move from higher energy states to lower ones, while using some of that drop-in energy to build and maintain complex structures. On a rogue planet, there is almost no external light, but there is still internal energy, heat flowing outward, chemical gradients generated where rock, water, and possibly gases interact. If such a world hosts a subsurface ocean, separated from space by a thick shell of ice, the interface between that ocean and the rocky mantle below becomes a natural site for hydrothermal systems. Water percolating into the rock can interact with minerals, driving reactions that release hydrogen gas and other reduced species. These can then mix with more oxidized components in the surrounding water, creating energy gradients similar in spirit to those at Earth's deep sea vents. In this way, a rogue planet's internal heat and geochemistry could support chemosynthetic life. Even in complete darkness, the stability of such environments is shaped by the same factors we explored earlier: radioactive decay providing long-term heating, thick ice or atmospheres providing insulation, the slow, persistent nature of internal heat flow. Under a sufficiently thick ice shell, a subsurface ocean can be shielded from the external environment, protected from micrometeorite impacts, from radiation bursts, from variations in the interstellar medium. The ice acts as both barrier and insulator, holding in heat, keeping temperature and pressure relatively stable over long timescales, potentially much longer than the surface stability of many planets that orbit stars. Where stellar evolution, asteroid impacts, and atmospheric loss can cause more drastic changes. If we imagine a rogue planet of roughly Earth's mass, with a deep global ocean hidden under ice and an actively convecting mantle below, we can picture hydrothermal vents dotting the ocean floor, each vent acting as a local source of chemical energy, surrounded by gradients in temperature and composition. In such an environment, microbial life could, in principle, emerge or persist, using chemosynthesis as an energy source, just as vent communities on Earth do. Whether life actually could originate in such settings is a deeper question. But the basic ingredients are there: liquid water, a supply of energy from chemical reactions, a variety of minerals and dissolved species, long timescales of relative stability, and physical isolation from violent surface events. Some origin of life scenarios on Earth already place the earliest steps of biology near hydrothermal systems, where steep gradients and complex mineral surfaces might have helped concentrate and organize prebiotic molecules. If something similar can happen on a sunlit planet, it is not unreasonable to consider that it might also happen on a sunless one, provided the necessary chemistry and energy flows exist. There is also another possibility. Life might not start on a rogue planet, but arrive there. The idea that life or its building blocks can travel between worlds is called panspermia. Fragments of rock blasted from planetary surfaces by impacts can sometimes escape their home worlds. They can drift through space, potentially carrying dormant microorganisms or organic molecules within them. If such a fragment is later captured by another planet, it might seed that world with new chemical or biological material. A rogue planet, with thick ice or deep oceans, could act as a receiver in this process, capturing material from passing comets, asteroids, or debris from other systems it happens to cross near during its long journey. Conversely, a planet ejected from its system while already hosting life, perhaps in subsurface oceans or underground habitats, could become a kind of interstellar arc. As it drifts between stars, its interior remains warm and shielded, preserving whatever life it carries for millions or billions of years, far longer than an unprotected rock exposed directly to space. In this view, rogue planets might serve as reservoirs or carriers of life, transporting living systems, or prebiotic chemistry, across large galactic distances. Regardless of how life might appear on such worlds, either emerging independently or arriving from elsewhere, its adaptation to eternal darkness would be profound. Without a sky that brightens and fades, there would be no natural circadian rhythms linked to light. Temporal patterns might instead follow other cycles, such as chemical fluctuations near vents, slow changes in local temperature, or internal biological clocks. Senses based on vision would be limited. At best, life might use bioluminescence, generating its own light for communication or hunting, as some deep-sea organisms on Earth do, but vision would not dominate the way it does in many surface ecosystems here. Other senses, sensitive to chemistry, pressure, or subtle changes in flow and vibration, might be more important. In a subsurface ocean, life could flourish entirely within liquid water, never encountering open air or sunlight, its entire evolutionary history unfolding under kilometers of ice, supported by the steady, deep-time energy of the planet's interior. The potential longevity of such habitats is striking. Stars change over time, their luminosity increases. Their output of high-energy radiation varies. Events such as supernova explosions or intense flares from nearby stars can alter environments on planets that depend on light. But the internal heat of a planet declines slowly and predictably as radioactive isotopes decay. The timescales involved can span many billions of years, longer than the main sequence lifetimes of some stars, especially more massive ones. This suggests that internal oceans on rogue planets could remain stable for periods of time that rival or exceed the habitable lifetimes of many illuminated worlds. In addition, because these habitats are shielded by ice or atmosphere, they are less vulnerable to external catastrophes, such as gamma-ray bursts or intense ultraviolet radiation from passing hot stars. In this sense, rogue planets may offer some of the most durable refuges for life in the galaxy. Quiet, dark, but stable. There is one more subtle factor to consider: the possibility of temporary external boosts. As a rogue planet moves through the galaxy, it may occasionally pass through denser regions of gas and dust, such as the outer edges of molecular clouds, or through regions where there are more nearby stars. In those areas, the total flux of radiation reaching the planet from distant stars and diffuse emission could increase slightly, not enough to create a true day, but enough to alter the energy balance of the outer layers. If the planet retains an atmosphere, additional external radiation might warm the upper atmosphere, changing circulation patterns, perhaps altering how heat flows from interior to space. These effects would likely be modest, spread across very long timescales, but they add complexity to the planet's thermal and chemical environment. Cosmic rays and high-energy particles may also vary along the planet's path. Passing through regions influenced by supernova remnants or active stellar associations could change the rate at which molecules in the upper atmosphere or ice are broken apart and reformed. This could slowly modify the inventory of chemicals available at the surface or ocean interface. In principle, such variations might provide additional energy gradients or new chemical ingredients for any life that exists below. Though the details would depend delicately on the planet's structure and composition, when we put all these pieces together, a coherent picture emerges. Life without sunlight is not only possible in theory, it already exists in partial form on Earth, in deep ocean vents, subglacial lakes, and underground ecosystems that do not depend on direct starlight. A rogue planet with internal heat, subsurface oceans, and active geochemistry could provide an even more extreme version of such an environment, extensive, global, and long-lived. In the warm waters beneath its ice, microbes might harvest chemical energy from hydrothermal vents, building organic molecules and establishing food webs. Over immense spans of time, evolution could produce diverse ecosystems, perhaps never aware that beyond their ice ceiling lies the emptiness between stars. From outside, the planet would appear almost completely dark, a faint infrared glow against the cold background, with no visible sign of the complex chemistry or possible biology hidden within. For a listener easing into sleep, there is a deep, quiet wonder in this possibility that in the most remote and silent places, in worlds cast off from their stars, there could still be warmth and water and life, not illuminated by any dawn, but sustained by the slow, patient fire of radioactive decay and the interplay of rock and water in the dark. You can imagine that now, an ocean under ice, on a world no star ever rises over. Yet within that ocean, countless microscopic lives, moving slowly, metabolizing, dividing, dying, evolving, completely indifferent to the absence of a sky. Their universe is the water around them, the gradients of temperature and chemistry near vents, the solid seafloor below, the ice above. Everything beyond that is irrelevant to their existence. And yet, from our wider perspective, we can see the whole structure, a warm interior, a liquid ocean, a frozen shell. Surrounded by the cold vacuum of interstellar space, drifting through the galaxy on a path that spans hundreds of millions of years. In such a vision, rogue planets are no longer just lonely, they are potential sanctuaries, islands of habitability scattered through the darkness, each one a sealed, self-contained experiment in chemistry and evolution. As you breathe slowly and let your thoughts soften, you can rest with this idea that life, if it exists there, does not depend on brightness or spectacle. It depends on gradients, on flows of energy from high to low, on stability over long timescales, all of which a sunless planet drifting between the stars can quietly provide. In the darkness between the stars, worlds without suns do not announce themselves. They do not shine, they do not flare, they do not bathe nearby space in light. They are almost perfectly black, radiating only a faint thermal glow, like embers buried under a thick blanket. From our vantage point on a bright, sunlit planet, trying to detect such worlds is like trying to find a single, unlit grain of sand floating in a vast, dark ocean, seen from unimaginable distance. To understand why, we can start with something simple. Our eyes, and the telescopes we first built, are most sensitive to visible light, the kind of light that stars produce in abundance. The sun pours energy across a broad spectrum, with a significant fraction in the range our eyes evolved to see. Planets in orbit around such stars do not emit much visible light themselves, but they reflect starlight. They shine by borrowed radiance. Even then, they are faint compared to their stars. A planet like Earth is billions of times dimmer than the sun in visible light. Detecting it directly against the glare of its star is extremely difficult. It requires careful techniques, special optics, and often the favorable geometry of a transit. When the planet passes in front of the star, now imagine removing the star entirely. A rogue planet has no nearby sun to illuminate it. There is no bright source for it to reflect. No disk of light behind which we can see a transit. In visible wavelengths, it is almost completely dark, a black sphere against a black background. From Earth's perspective, there is no contrast to work with. The object does not glow in the optical range, and it does not block out any nearby bright source on a regular schedule. It simply drifts. This is why such planets are nearly invisible to traditional optical surveys. Yet they do have one thing we can exploit: gravity. Even if a rogue planet emits no light, its mass still warps the space around it. In the language of general relativity, mass and energy curve spacetime, and curved spacetime tells light how to move. When a compact mass passes in front of a more distant star, its gravity can bend the light from that star, focusing it slightly toward us. This effect is called gravitational lensing. In extreme cases, where the lens is a galaxy or a cluster of galaxies, the effect can be dramatic: arcs of light, multiple images, magnified views of distant quasars. When the lens is only a planet, the effect is far more subtle, but it is still real. We call this gravitational microlensing. Imagine a distant star, far beyond our solar system. Its light travels in nearly straight lines through space, heading toward our telescopes. Now imagine that, by chance, a rogue planet drifts across the line of sight, not necessarily in front of the star's disk, but near enough that its gravitational field significantly bends the nearby light paths. For a short period of time, the star's apparent brightness as seen from Earth increases. The planet's gravity acts like a weak, temporary lens, magnifying the light. There is no transit shadow, no dimming. Instead, the star gently brightens, then slowly returns to normal. The shape of this brightening, how quickly it rises and falls, how long it lasts, carries information about the lens. For a single, isolated lens, the most basic microlensing light curve has a characteristic symmetric shape. It brightens smoothly to a peak when the alignment is closest, then fades symmetrically as the lens moves away from the line of sight. The timescale of this event depends on the mass of the lensing object and its relative motion. Stars produce microlensing events that can last weeks to months. Planets produce shorter events, sometimes only days or even less. By monitoring large numbers of stars and carefully measuring their brightness over time, astronomers can detect these brief, subtle magnifications from them. They can infer the presence of unseen lenses, including rogue planets. Microlensing has several powerful features and several limitations. It does not depend on the planet emitting or reflecting any light, only on its mass, so even cold, dark planets can be detected. It is also sensitive to planets at a wide range of distances from Earth, even in the inner regions of the galaxy, as long as there is a bright background star behind them. But microlensing events are rare. The alignment required is very precise. The planet must pass almost exactly in front of the distant star as seen from our vantage point, and each event is a one-time occurrence. Once the alignment is gone, the same lens source pair will not produce another event on human timescales. This makes follow-up difficult. We detect the existence of the lens, but we do not usually see it directly afterward. We measure its mass only approximately, and we learn little about its composition, its atmosphere, or any surface conditions. Still, by collecting many microlensing events, astronomers can build statistical models. They can estimate how many planet mass lenses are needed to explain the observed frequency and distribution of events. From this, they infer that there may be a vast population of free-floating planets in the galaxy. Some studies suggest that there may be at least of order one rogue planet for every star, perhaps more. The exact numbers remain uncertain, but the implication is clear. The Milky Way is likely full of these dark wanderers. Microlensing is not the only tool we have. If a rogue planet is young or massive, it may still retain enough internal heat to glow more strongly in infrared wavelengths. This emission is thermal, determined by the planet's temperature. Hotter objects radiate more, and at shorter wavelengths, cooler objects radiate less, and mostly at longer wavelengths. Space telescopes designed to survey the sky in the infrared can therefore pick out isolated, cool objects that do not correspond to known stars. Missions such as the Wide Field Infrared Survey Explorer, often shortened to WISE, have mapped the sky at several infrared bands. These surveys have discovered many brown dwarfs, objects with masses between those of giant planets and small stars, which never ignite sustained hydrogen fusion in their cores. Some of the faintest, coldest brown dwarfs discovered have temperatures only a bit warmer than room temperature. They approach the regime of giant planets in both mass and thermal emission. Distinguishing a very low-mass brown dwarf from a very massive rogue planet can be challenging. The line is not perfectly sharp. One approximate guideline is whether an object was or was not massive enough to briefly burn deuterium, a heavier isotope of hydrogen, in its core above a certain mass threshold of roughly a dozen times the mass of Jupiter. An object can sustain limited deuterium fusion early in its life. Below that threshold, it cannot. By this criterion, objects below that limit are more comfortably labeled planets. Those above are more comfortably called brown dwarfs. But when we look at an isolated, cool object in the sky, we almost never know its full history. We infer its mass from models of its luminosity and temperature, which depend on age and composition, parameters that are not always well constrained. As a result, some of the objects we classify as free-floating planetary mass bodies might be on the border between planets and brown dwarfs. Others are more clearly in the planetary regime, but in either case, they demonstrate that the universe produces many isolated, non-stellar bodies with masses in the planet range. Future missions take this approach further. Telescopes such as the Euclid mission and the Nancy Grace Roman Space Telescope are designed to conduct wide-field surveys with exquisite sensitivity and resolution. Roman in particular is expected to carry out dedicated microlensing campaigns toward the center of the galaxy, monitoring hundreds of millions of stars for tiny brightness variations. Its sensitivity should allow it to detect microlensing events caused by planets as small as Mars, including free-floating ones. By combining high-cadence microlensing observations with precise measurements, such surveys can dramatically improve our estimates of the rogue planet population. They can probe both bound and unbound planets across a wide range of masses and distances. At the same time, infrared instruments on these and other telescopes will continue to search for the faint thermal signatures of isolated cool objects, expanding the catalog of candidate free-floating planets and very low-mass brown dwarfs. Another complementary technique involves astrometry, the precise measurement of star positions over time. A massive object passing relatively near our line of sight to a star can cause not only a microlensing brightness change, but also a tiny shift in the apparent position of the star on the sky. This is called astrometric microlensing. With sufficiently accurate position measurements, it becomes possible to better constrain the mass and distance of the lens, potentially distinguishing more clearly between stellar, brown dwarf, and planetary mass lenses. Missions such as Gaia are already mapping the positions and motions of over 1 billion stars with high precision. Astrometric data combined with photometric microlensing measurements could eventually provide more detailed information about individual rogue planets, not just their approximate masses, but also their distances and trajectories. Despite these tools, challenges remain. Cold planets that are old and of only moderate mass emit very little infrared radiation, too little for current surveys to detect at large distances. Their microlensing events are brief, easy to miss without constant monitoring, and once an event is over, the lens vanishes again into darkness. Theoretical population estimates rely on combining incomplete data sets, microlensing statistics, infrared luminosity functions, simulations of planetary system evolution, each with their own uncertainties. Nevertheless, the convergence of multiple lines of evidence suggests that ejection of planets is common, and that the cumulative result is a large background population of rogues. When numerical models simulate the early evolution of planetary systems with multiple giant planets, they frequently eject a fraction of them into interstellar space. When they include smaller planets, these are often even more easily lost, their low mass making them more susceptible to gravitational scattering. If nearly every star system forms several planets, and if a significant fraction of those systems eject one or more planets over their lifetimes, the total number of rogue planets in a galaxy with hundreds of billions of stars can become very large. Some estimates suggest that for each star, there may be a comparable number of free-floating planets, or even several times more. The exact ratio is still debated, but it is unlikely to be tiny. This raises an intriguing question. How many such worlds might be passing near our own star at any given time? Near in galactic terms does not mean close enough to see in a backyard telescope. It may mean within a few light years, or within the local volume defined by the Sun's neighborhood in the Milky Way. If rogue planets are as common as many models suggest, then within a sphere of radius a few dozen light years around the Sun, there could be dozens, hundreds, or even thousands of such objects, most of them completely unknown to us, drifting silently through the shared galactic environment. The probability that one of these planets would pass extremely close to the Sun, close enough to significantly perturb our own planetary system, is very low on human timescales, but over the full lifespan of the galaxy. Such close encounters are not impossible. More commonly, rogue planets simply share the general flow of stars and gas around the galactic center, passing at distances of many light years, too far to have strong gravitational effects on any one system, but close enough that, in principle, our instruments could detect their faint thermal glow or their gravitational influence in microlensing events, from the perspective of a listener resting, letting the mind drift. There is a strange, gentle comfort in this picture. The sky you see at night, filled with stars, is only the visible part of the local environment. Between those stars, in the nearly invisible darkness, there may be many planets, each one a silent traveler, carrying its own history of formation and ejection, its own internal structure, its own potential for oceans and perhaps even life, yet almost entirely hidden. We know of them not because we see them directly, but because gravity betrays them, because the path of light from distant stars is ever so slightly bent, because the infrared spectrum of the sky contains faint, cool signatures of solitary masses. Searching for these worlds requires patience and persistence. Surveys must monitor huge numbers of stars, night after night, looking for tiny changes in brightness that could signal a microlensing event. Analysis pipelines must sift through vast quantities of data, separating intrinsic stellar variations from lensing signals, characterizing each event, estimating the likely mass of the lens. Infrared telescopes must scan large swaths of sky, identifying dim sources, measuring their colors and motions over time, distinguishing nearby cool objects from distant galaxies, separating brown dwarfs from planetary mass bodies. It is slow, careful work, yet as our instruments improve, the veil gradually thins. What was once pure speculation becomes constrained by observation. The population of rogue planets transitions from theoretical necessity to measured reality. For now, most of these worlds remain out of reach. Each detection is a brief, passing glimpse, a temporary brightening, or a faint infrared dot at the limit of senses. But the trend is clear. Future surveys will find more. Microlensing campaigns from space, combined with ground-based efforts, infrared and astrometric measurements, all will contribute to a richer map of the galaxy's dark planets. As you lie here, breathing slowly, you can imagine this observational effort as a kind of gentle, patient listening. We aim our telescopes at the sky and watch, quietly, for the universe to whisper through tiny changes in starlight, through subtle shifts in position, through barely perceptible warmth in the infrared. Each whisper says, "There is a mass here. There is a world here. It does not shine, but it exists." In that way, even the most isolated rogue planet leaves a trace, not in bright color or dramatic appearance, but in the way it slightly rearranges the flow of light and contributes to the overall structure of the galaxy. The cosmos is not only the stars we see, it is also the invisible architecture of dark planets, brown dwarfs, gas clouds, and dark matter, all interacting gravitationally over immense spans of time. Learning to detect rogue planets is learning to see that hidden architecture, to recognize that between the bright points of the sky, there is a rich population of unseen worlds, drifting. You do not have to hold all the technical details in your mind as you fall asleep. You can simply rest in the knowledge that, all around our sun, across distances of many light years, there are likely other planets, starless, cold on the outside, perhaps warm within, moving silently through the same galactic disk we inhabit. We glimpse them only occasionally. Through microlensing, through infrared surveys, through the refined measurements of future missions. But whether we see them or not, they are there, drifting, obeying gravity, circling the center of the Milky Way on orbits that take hundreds of millions of years to complete, writing their presence into the galaxy not with light, but with mass and motion. And somewhere out in that darkness, a rogue planet continues its quiet journey, undetected by our instruments. For now. Yet fully real, a complete world in its own right. Imagine yourself standing on the surface of a world where dawn will never come. No hint of sunrise waits below the horizon, no slow brightening of the sky, no daily rhythm of light and shadow. There is only darkness. But this darkness is not a simple blank. It is layered, textured, shaped by the physics of a planet drifting without a star. If you stood on such a world, what would the sky look like? On Earth, we are used to a blue daytime sky. Produced by sunlight scattering off air molecules, we are used to a night sky in which stars are set against a dark background, with the faint band of the Milky Way crossing overhead. On a rogue planet, there is no daytime sky at all, no sun to scatter, no bright disk to outshine the stars. If the planet has an atmosphere, the sky would not be perfectly black. Even in darkness, molecules in the air can scatter starlight and emit faint glows from chemical processes and interactions with cosmic rays. There might be a subtle, persistent dimness, a kind of almost black twilight, but it would never rise to the brightness of day as we know it. The color of this sky would depend on the composition of the atmosphere. In a thin, clear nitrogen and oxygen atmosphere, like Earth's, the sky might remain nearly black, with only the stars and the Milky Way truly visible. In a dense hydrogen atmosphere, the scattering behavior would be different, possibly giving a faint, deeply muted tint at certain wavelengths. But still, no bright dome of color. What would dominate the sky is the galaxy itself. Without a local star to blind you, your eyes would adapt to the dark. You would see the Milky Way as a bright, structured band stretching across the sky, its central bulge and spiral arms resolving into countless stars, clouds of dark dust cutting lanes through that glow. If your rogue planet lay within a relatively dense part of the galactic disk, the star field would be rich. Everywhere you look, pinpoints of light, some brighter, some fainter, a cold, diamond dust scattered across the black. These stars would not rise or set in the usual sense, because the only significant motion would be the planet's slow rotation and the gradual drift of its orientation over time. You might still have a local rotation period, a day defined by how long the planet takes to spin once, but that rotation would not produce a cycle of light and darkness, only a gentle, slow turning of the star field overhead. Instead of a sunrise, you might mark time by the passage of particular bright stars or clusters across the sky. Perhaps a dense region of the Milky Way would arch from horizon to horizon once each rotation. But the brightness contrast between overhead and below the horizon would be subtle. The whole experience would remain firmly in the realm of night. The starlight itself would feel cold. On Earth, sunlight warms your skin. You can feel its heat directly. Starlight from other stars is too faint to notice physically. Even if you could see their colors, the energy they deliver is negligible. On a rogue planet, this is even more true. Every star is a distant point, no single one bright enough to cast sharp shadows. The combined starlight from all directions would still carry little energy compared with the planet's internal heat. You might hold out your hand and see it only as a silhouette against the star field, unless some local source of light illuminates it, a vent, a glow from the ground, lightning in a thick atmosphere, or artificial lights if a civilization were present. Now consider the landscape itself. There are two broad extremes to imagine. One is a world whose surface has largely frozen, with most volatiles locked into ice, its atmosphere perhaps thin or partially collapsed. The other is a world with a thick, deep hydrogen atmosphere, where surface temperatures remain above the freezing point of water, kept warm by internal heat and greenhouse trapping. On the frozen world, you might stand on a plain of ice that stretches for hundreds of kilometers. The surface is hard, dry, and bitterly cold. The temperature near the ground is not just below the freezing point, but potentially hundreds of degrees colder. Close to the equilibrium set by the cosmic microwave background and any residual atmospheric insulation, ice here is not just frozen water. It might include carbon dioxide ice, methane ice, or more exotic frozen gases. Depending on what the planet started with and how its atmosphere evolved, the ground could be cracked by thermal stress as the interior slowly shrinks and cools, forming ridges, faults, and jagged blocks. In some regions, impacts from small bodies drifting through interstellar space might pockmark the surface with craters. Though the rate of such impacts is much lower than in dense asteroid belts, the surface could remain relatively unchanged for millions of years. If you walked across this terrain, the crunch under your feet might be faint in the thin atmosphere. Sound would carry poorly. High-frequency components would die quickly, leaving only low, muted tones. Acoustic silence would be one of the most striking sensations. Without wind or waves or biological noise, you might hear only your own footsteps, your own breathing, the occasional crack of shifting ice, and the distant groaning of slowly moving crustal plates. If plate tectonics is still active, because even a rogue planet can have tectonics, plate tectonics depends primarily on internal heat and mantle convection, not on sunlight. If enough heat flows from the interior toward the surface, and if the lithosphere is weak enough to break into plates, those plates can still slide past one another, subduct, and generate mountains and trenches. On a frozen rogue planet, tectonic activity might be slower than on Earth because the overall heat flow might be lower, but over geological timescales, it could still reshape the surface. Mountains might rise under a perpetually dark sky, snowless peaks of bare rock and ice, their outlines sharp against the star field. Volcanic eruptions might pierce the cold crust. vent molten rock and gases into the thin atmosphere, forming local plumes of warmth and possibly temporary atmospheres of vapor, before radiation and condensation freeze everything back down. Weather on such a world would be driven not by solar heating, but by internal heat leaking through the crust, and by the slow redistribution of that heat through an atmosphere that may be thin but still present. Imagine a planet with a modest atmosphere, mostly nitrogen and carbon dioxide. Surface temperatures everywhere are extremely cold, but some regions above shallow magma reservoirs are slightly warmer. There, gases may rise slowly, creating gentle convection cells, winds that drift along the surface, carrying tiny amounts of heat and dust, because the temperature contrasts are small, and because radiative cooling is efficient. These winds would be weaker than typical storm systems on Earth, more like slow, persistent breezes than violent storms. Yet over long periods, they could transport fine particles, sculpting dunes of frozen grains, or carving subtle patterns into the ice. In contrast, on a warm rogue planet with a thick hydrogen atmosphere, the experience would be very different. Beneath that deep blanket of gas, pressure at the surface could be tens, hundreds, or even thousands of times Earth's atmospheric pressure. The air would not be breathable for us, but its physical behavior would be well described by the same fluid dynamics that govern Earth's atmosphere. Here, internal heat flux from below and radiative cooling from the upper layers drive circulation. Warm gas near the surface rises, cools as it moves upward, then spreads and eventually sinks again, creating overturning cells somewhat analogous to Hadley circulation on Earth, but powered from within instead of from above. Clouds could form in such an atmosphere, not necessarily water clouds, but clouds of various condensable species depending on temperature and composition, ammonia, methane, water, or more complex hydrocarbons. These clouds might be thick and multi-layered, glowing dimly in thermal infrared, but effectively opaque to human eyes in the absence of external light. If you were on the surface of such a world, you might not see the stars at all. The sky could be a dark, featureless ceiling of thick cloud, with no visible structures unless lightning or other energetic events illuminated the layers. Instead of a starry canopy, your environment might feel more like the interior of a vast, warm, misty cavern with high-pressure air pressing in from all sides, and winds flowing slowly in response to internal heating patterns. In that case, the primary natural light sources could be volcanic eruptions, or hot vents where molten rock or superheated water reaches the surface. At these locations, the ground might glow dull red from heat, casting faint illumination on the nearby terrain, plumes of gas and ash rising into the heavy atmosphere, generating local weather disturbances, clouds of condensation, and gusts of wind driven by buoyancy on both types of rogue planet, frozen or warm. Volcanism can be the dominant source of visible light. Imagine walking towards such a region on a dark, frozen world. At first, the landscape is lit only by distant stars. Everything around you is dim, edges softened by the lack of strong shadows. Then, ahead on the horizon, you see a glow, a faint, orange-red smear against the black sky. As you approach, you realize that it comes from a fissure in the ice or a volcanic cone, where molten material from the mantle reaches the surface. Near the fissure, the ice is melted or vaporized, exposing rock below. Gases roar out, then cool and crystallize into new deposits, a local storm of heat and chemistry embedded in an otherwise frigid world. The air here, if there is air, would carry more sound. You might hear the deep resonance of the vent, the hissing of escaping gas, the crackling of rapidly cooling rock. Above the vent, plumes can drive convection in the atmosphere. Warm parcels of gas rise rapidly, dragging cooler air in from the sides. These motions can create winds, jets, and even large-scale circulation patterns if the heat source is extensive. Thus, on a rogue planet, winds are often driven from below. Instead of solar heating of the upper atmosphere, you have geothermal heating from the interior, directed upward through localized sources. The pattern of winds would therefore trace the distribution of internal activity, flowing from volcanic hotspots toward cooler regions, and sinking where the atmosphere radiates heat away into space. Over a subsurface ocean world, the situation becomes even more interesting. Picture yourself not on the ice surface, but in a theoretical sealed habitat placed on an ice plain above a global ocean. You walk across ice that is perhaps several kilometers thick. Beneath your feet, pressure is high. The ice at depth is warm and ductile. Below that lies a liquid ocean kept above freezing by heat from the interior. The feeling of walking across such a plain, if you could do so safely, might be subtly different from walking on solid rock. The ice shell could flex under large-scale stresses, rising and falling slightly over time as mass redistributes. Across years or centuries, surface features might slowly creep, fractures might open and close, ridges might form where ice plates converge. If you could see into one of those fractures, perhaps through a naturally opened chasm, you might glimpse the glow of warmer material below, or the faint shimmer of liquid water at depth, illuminated by thermal radiation from the interior. A reminder that beneath the seemingly dead surface, there is movement and potentially habitable environments. The psychological effect of such an environment would be profound. On Earth, even at night, we live with the expectation of dawn. We know that the world will brighten again, that sunlight will return, bringing warmth and color. On a rogue planet, there is no such expectation. Night is the baseline, the default state. Any local light, from volcanism, from lightning in a thick atmosphere, from bioluminescent organisms if they exist, or from artificial sources, is a temporary and localized deviation from the rule of darkness. The horizon would be a sharp, black curve, marked only by the silhouettes of mountains or ice ridges against the star field. There would be no auroras from a solar wind, though interaction with the galactic cosmic ray background and any planetary magnetic field could generate more subtle phenomena. At most, faint glows high in the atmosphere from charged particles spiraling along field lines, over extremely long timescales. The night sky itself would change. As the planet moves around the galaxy, the pattern of stars slowly shifts, clusters move, spiral arms come into and out of view, but these changes unfold over millions of years, far longer than any human lifetime. So for all practical purposes, the sky is fixed. The overall impression is one of eerie calm. Even if interior processes are active, even if tectonics reshapes the crust, even if weather slowly circulates gases, all of it is wrapped in a silence and darkness that are nearly absolute, broken only by rare, localized anomalies of light and sound. For someone standing there, the universe would feel vast and remote. Every star a distant sun with its own system, every point of light separated from you by many trillions of kilometers. Almost nothing in your immediate environment would change quickly. Time would feel stretched, your own heartbeat and movement among the few things that happen on a human scale. Yet beneath this surface stillness, thermodynamics and gravity continue their work. Heat flows from interior to space, mantles convect, ice shells deform, atmospheres circulate, oceans perhaps churn slowly above warm rock. The planet is not dead, it is simply quiet. Its most dramatic processes occurring at energy levels and timescales that do not demand spectacle. As you breathe slowly now, you can imagine that quiet, a world with no sunrise, a sky filled with cold stars, or perhaps hidden by thick, dark cloud, landscapes of ice or rock, frozen into shapes that change only over geological ages, or wrapped in warm, high-pressure atmospheres where internal heat drives slow storms. You feel the ground under your feet, solid. Yet above a deeper, flowing interior, you feel the air, thin and brittle, or dense and heavy, but always dim, always lit only by the faintest natural sources, except where gravity and heat force small pockets of light into existence. In that calm, you stand on a rogue planet, one of countless starless worlds, drifting between the suns of the Milky Way. Picture the Milky Way as seen from far above, a vast, flattened disk of stars, gas, dust, and dark matter, slowly rotating around its center. Within that disk, countless orbits weave and overlap. Stars move along nearly circular paths, wobbling slightly up and down through the galactic plane. Clouds of gas drift and compress and form new stars. Clusters slowly disperse, and among all of these there are planets. Some are bound to their stars, tracing small, tight loops around them, riding along as the whole star system orbits the galactic center. Others, the rogue planets, are not bound to any star at all. They follow their own paths, dictated by gravity alone, yet still shaped by the overall potential of the galaxy. If you look at the motion of a single rogue planet from a high vantage point, Far above the galactic disk, you would see it tracing a long, graceful orbit around the center of the Milky Way. In broad terms, its path would resemble that of a star at a similar distance from the center, an almost circular or mildly elliptical track, taking hundreds of millions of years to complete one full revolution. For a planet located roughly where our Sun is, that orbital period is on the order of a couple of 100 million years. Human history is a tiny fraction of such a timescale. Entire species can come and go while the galaxy completes only a small arc of one spin. A rogue planet shares in this slow galactic rotation, carried along by the same gravitational pull from the combined mass of stars, gas, and dark matter, but superimposed on this broad orbital motion are smaller deviations. The planet may oscillate slightly above and below the galactic plane, spending part of its time in the denser midplane where most stars reside, and part of its time in regions with fewer stars, less gas, more open space. It may also experience gentle radial motions, moving a little closer to the galactic center over some segments of its orbit, then drifting slightly farther away, like a bead sliding along a slowly vibrating wire. These oscillations are governed by the gravitational structure of the galaxy, by how mass is distributed, and by past encounters with stars, clusters, and clouds. From the planet's own perspective, none of this is obvious. Standing on its surface, you would simply see the sky of stars, changing only imperceptibly over human lifetimes, perhaps on the scale of millions of years. The relative positions of constellations would shift, new clusters would enter view. Some regions of the Milky Way would appear brighter or darker, but to any civilization or observer living for only a few centuries, the sky might seem fixed. Yet over the full span of a galactic orbit, the rogue planet will encounter different environments. As it moves through the spiral pattern, it may pass through or near spiral arms, regions where gas and young stars are somewhat more concentrated. Between those arms, it moves through more diffuse interarm space. Spiral arms are not solid structures. They are patterns formed by density waves, regions where material slows down slightly, becoming more crowded, then speeds up again, moving on. As the rogue planet crosses an arm, the local density of stars around it may increase modestly. The background radiation field from starlight may brighten a little. The chance of passing relatively near a star or a molecular cloud becomes slightly higher, though still small on human scales. Most of the time, even in a spiral arm, distances between individual stars remain enormous. To get a sense of scale, if you shrank the sun to the size of a single grain of sand, placed somewhere on a large field, the nearest star would be another grain of sand many kilometers away. A rogue planet moving through such a sparsely populated environment is unlikely to come extremely close to any star, but over hundreds of millions or billions of years, chances accumulate. It may pass within a few light years of a star, close enough for that star to appear somewhat brighter in its sky than most others, yet still far too distant to dominate the planet's environment. The planet would remain in darkness, perhaps with a slightly more prominent bright star in its heavens for a few tens of thousands of years. Before moving on rarer occasions, a rogue planet might have a closer encounter. Gravitational encounters between free-floating planets and stars can lead to a range of outcomes. In most cases, the planet simply has its trajectory bent, its velocity vector altered by a small amount. It swings past the star, then continues on a new path, still unbound, still wandering, but under very specific conditions. If the relative velocity is low enough and the geometry favorable, the planet can be captured. It might become a new, distant member of the star's planetary system, falling into a wide, elongated orbit, or perhaps eventually being perturbed again and ejected anew. The reverse is also possible. A planet originally bound to a star system can be stripped away by a close encounter with another star. Adding to the rogue population, simulations of stellar clusters and galactic dynamics suggest that such capture and ejection events are not common outcomes in any single close pass. But the galaxy has had billions of years and enormous numbers of stars and planets, so even rare processes can contribute significantly to the overall statistics. Still, for any one particular rogue planet, the probability of being captured by another star during a single galactic orbit is very low. Most will spend their entire existence as free floaters, unbound, responding only to the smooth gravitational field of the Milky Way, and the occasional distant tug from passing masses. Over time, their orbits may slowly diffuse. Scattered by weak encounters with stars and giant molecular clouds, they might drift inward toward the galactic center, or outward toward the fringes. They might gain or lose orbital energy in small increments, their paths gradually changing. In this sense, rogue planets are interstellar messengers, not because they carry information in the way a probe does, but because their trajectories weave together the history of different parts of the galaxy. A single rogue planet might have formed near one star, been ejected during a chaotic early epoch, passed through several spiral arms, skimmed the outskirts of clusters, crossed paths with many other stars, and eventually drifted into an entirely different region of the Milky Way. Inside its rocks and ice, isotopic ratios and chemical patterns would record its birthplace. Its early formation conditions, its exposure to cosmic rays over eons, its thermal history as internal heat slowly declined. If an advanced civilization ever intercepted such a world and studied it in detail, they might read its internal record as a kind of geological and astrophysical diary, a logbook of conditions in distant star-forming regions long ago. Most rogue planets will never be studied this way. They will simply continue their long journeys, unobserved, unvisited. But the concept remains. Each one is a traveler bearing silent testimony to the processes that shape planetary systems and throw some worlds into interstellar space. The timescales involved are almost beyond direct intuition. Consider again a single orbit around the galactic center, on the order of a few 100 million years. During that time, entire mountain ranges on Earth can rise and erode away. Continents can drift thousands of kilometers. Species can evolve, diversify, and go extinct. Now imagine a rogue planet completing not just one galactic orbit, but 10 or 20. That corresponds to billions of years. Over such spans, stars like the Sun live out almost their entire main sequence lifetimes. Massive stars form and explode as supernovae, enriching the interstellar medium with heavy elements that will build the next generations of planets. Through all of this, a rogue planet can persist. Its internal heat slowly decreases. Its possible oceans may gradually freeze. Its atmosphere may change as volatiles condense or escape. Yet the planet itself remains, a stable gravitationally bound object, coasting through the evolving galaxy. In many cases, a rogue planet may outlive its parent star. The star that once illuminated it may swell into a red giant, shed its outer layers, and end as a white dwarf, gradually cooling over time. Meanwhile, ejected long before that final phase, the planet continues on its independent path, its original sun now just one unremarkable star among many in its sky, if it is even still in view. From the standpoint of the planet, forever is not truly infinite, but it is long enough that the end state of the universe becomes relevant. Over tens of billions of years, galactic structure may change, star formation will slow, stellar populations will age, yet free-floating planets will still exist. Cooled perhaps to very low temperatures, their internal heat nearly exhausted, but still gravitationally intact. In the far future, when most stars have faded, dark planets and stellar remnants may dominate the mass budget of the galaxy. The Milky Way then would be more like a graveyard of cooled objects, slowly orbiting in deep time. From where we are now, relatively early in cosmic history, we see only hints of that eventual state. But rogue planets give us a small glimpse of what a starless universe might look like. To return to the present, imagine following one particular rogue planet along its galactic journey. At one moment in time, it is moving through a relatively quiet stretch of the disk. Few bright stars, sparse gas. The sky from its surface shows the Milky Way as a thin, moderately dense band. As millions of years pass, the planet's orbit carries it closer to a spiral arm. The density of nearby stars increases. The band of the Milky Way overhead becomes brighter, more structured. Perhaps a nearby cluster appears in the sky as a tight knot of blue-white stars. For a brief period, measured in tens or hundreds of thousands of years, the planet passes relatively near a massive molecular cloud, a region rich in cold gas and dust, where new stars are forming. From the planet's surface, this might appear as a dark patch in the Milky Way, where background starlight is absorbed by dust, or as a glowing nebula if illuminated by young hot stars nearby. The radiation environment might change slightly. the flux of cosmic rays might vary, but the planet remains internally dominated by its own heat. Then, gradually, it moves on, exiting the spiral arm, drifting back into a quieter region. Over successive orbits, the pattern repeats, though never in exactly the same way. Because the galaxy itself is evolving, spiral arms shift, clusters dissolve, molecular clouds form and disperse. The rogue planet is both participant and witness in this slow choreography. It responds to gravity, its path subtly adjusted by each encounter. It contributes its own tiny share to the overall gravitational field. Though its mass is negligible compared to that of stars and dark matter, all the while, its surface remains dark, its interior quietly cooling, its potential subsurface oceans persisting or freezing depending on details of its heat budget. From the perspective of a listener settling into sleep, there is something deeply peaceful about this image. A world, like a small, silent ship, sailing on a vast, invisible current around the galactic center, taking hundreds of millions of years to complete each circuit, with no urgency, no haste. Nothing about its journey is fast in human terms. Everything is measured in aeons, in timescales so long that even major cosmic events blend into a gentle background of change. You can imagine yourself on the surface of such a world, looking up at the dense star field, knowing that behind that quiet glitter, the planet and the entire neighborhood of stars are moving together around the galaxy, like tiny beads embedded in a rotating disk. You feel the ground beneath you, solid and still, yet you know that in a deeper sense, you are in motion, orbiting the galactic center at hundreds of kilometers per second. But the scale of the orbit is so large and the curvature so gentle that to you, it feels like perfect stillness. This is one of the central paradoxes of cosmic perspective. We are always moving, planets around stars, stars around galaxies, galaxies within larger structures, yet our moment-to-moment experience is one of stillness, of local calm. For a rogue planet, this paradox is even more pronounced. It does not have the reference point of a star in its sky, no rising and setting to remind any inhabitants of their orbit, only the fixed-looking star field and the subtle, almost imperceptible drift of patterns over immense times. In that sense, a rogue planet is a perfect symbol of quiet motion, always traveling, never arriving, tracing endless loops around the galactic center, while on its surface, darkness and silence prevail. As you rest, you can let your thoughts follow that path. A world, flung from its parent system long ago, now circling the galaxy, passing through spiral arms and inner arm spaces, near clusters and clouds, its interior slowly cooling, its possible subsurface seas quietly moving, its sky filled with distant suns that never rise, never set. It has no destination, no goal, only the long, patient journey dictated by gravity. And in the vastness of the Milky Way, it is not alone. There may be billions of such worlds, each one with its own orbit, its own thermal history, its own potential for chemistry and perhaps life, all drifting together through the same galactic night. When you breathe in, you can imagine drawing in that sense of large, slow motion. When you breathe out, you can let go of smaller worries tied to much shorter timescales. Somewhere, in the great disk of the galaxy, a rogue planet continues its orbit, unaffected by brief events on distant worlds like ours, its journey measured not in days or years, but in revolutions around the galactic center, quiet, enduring, moving endlessly through the deep, star-filled dark. Out in the dark between the stars, the galaxy turns on inhuman timescales, spiral arms drift, star clusters form and dissolve, gas clouds collapse, ignite, and fade. And in that vast, slowly changing structure, rogue planets continue to drift. Each one is small compared to a star, small compared to a galaxy, but each one is complete in itself, a full world with gravity, geology, chemistry, temperature gradients, and a long, quiet history. As you rest now, you can let your attention widen, beyond any one particular world, to the whole picture. Imagine the Milky Way seen from outside, a flattened disk with a bright central bulge, arms curling outward, laced with dust lanes and glowing nebulae, billions upon billions of stars scattered like frost on a window. Inside that disk, there are many known planets, orbiting their suns in familiar ellipses, some close to their stars, some far away, some in systems with multiple planets, some circling alone. But there is also another population, not bound to any star, not tied to any sunrise or sunset, rogue planets, orphaned worlds. They move through the same galactic potential, drawn by the same overall gravity, but they travel without a central sun to anchor them. Their paths are not small loops, but long, graceful orbits around the galactic center itself. When you zoom your imagination down from the global view, from the large-scale map of the galaxy, to one single rogue planet, you find a tiny pocket of detail, a rocky core, a mantle that may still convect, an outer shell of ice and rock. Maybe a deep, hidden ocean, sealed beneath kilometers of ice, maybe a thick, blanketing hydrogen atmosphere, holding in heat from the interior. Inside, radioactive elements still decay, releasing energy in small, steady amounts. Accretional heat from formation is still slowly leaking away. Perhaps residual tidal heat from an earlier epoch lingers in the interior. All of this combines to produce a gentle, long-lived outflow of heat. It is not dramatic. It does not produce the blazing brightness of a star, but it is enough to melt ice deep below, enough to sustain hydrothermal vents at the base of an ocean, enough to drive convection, weather, and tectonics over geological timescales, while the outside of the planet is dark and cold. Its interior is a place of motion, of gradients, of possible complexity from the surface. If a surface observer existed, almost none of this would be visible. They would see a sky with no sun, only stars, or they might see thick, dark clouds overhead, hiding the stars entirely, but still no daily light cycle, no sunrise, no sunset. The horizon would be lit at most by volcanic glow, or by distant lightning in a heavy atmosphere, or by faint starlight reflecting off ice or rock. And yet, even in this environment, there can be continuity and endurance. You can think of these worlds as long-term experiments in physical law. Once formed and ejected, they continue according to the rules of gravity and thermodynamics, quietly obeying the same equations that govern planets with suns, but under different boundary conditions. They show us that being alone in space does not mean being static. Even in isolation, processes continue, heat flows, materials phase change, crusts crack and heal, oceans churn if they exist at all. In a way, this mirrors your own inner life. From the outside, to someone seeing only a still body at rest, there may seem to be very little happening, yet internally, cells continue their work, chemistry proceeds, electrical signals move through the nervous system. Even as consciousness drifts towards sleep, the surface looks calm, the interior remains active, quietly. Now let your attention move from the physics of one world to the sheer number of them. Take a moment to recall that the galaxy contains hundreds of billions of stars, and that simulations and observations hint that the number of rogue planets may be comparable, or even larger. We do not know the exact ratio, but it is entirely plausible that for every star there is at least one starless planet, perhaps several, scattered through the disk. This means that the Milky Way is not just a galaxy of suns, it is also a galaxy of dark worlds. Most of them will never be illuminated by any nearby star. Most of them will never be visited or even detected. They will simply exist quietly for aeons. There is a kind of austere beauty in that idea. Worlds wandering without audience, without the spotlight of a sun, without any guarantee that anyone will ever know they were there. And yet, they still obey the same deep rules, still carve their slow paths through space-time, still generate heat within, still shape and reshape their own interiors. They are part of the universe's inventory of possibilities, part of its full expression of what matter and gravity can do. If some of them host subsurface oceans or thick insulating atmospheres, then some of them might even host life, life that would never see a sunrise, that would know nothing of starlight, that would take as given that the universe is dark and that warmth comes from below. Biology built on chemical gradients instead of photons. Communities clustered around vents and warm rocks, evolving slowly in stable environments that might last for billions of years. It is speculative. We do not know if such life actually exists, but the physics does not forbid it. The basic requirements of energy, solvent, and molecules are not limited to star-illuminated surfaces. So as you breathe calmly, you can hold this possibility loosely in your mind. Perhaps, right now, in some distant reach of the Milky Way, a rogue planet drifts through the dark, and far below its ice shell, in a hidden ocean, life has adapted to its particular gradients and chemistries. Those organisms would know only their local surroundings. They would have no concept of galaxies or stars or rogue planets. In the same way, there are aspects of the universe that we cannot see from our limited human perspective, structures and futures beyond our current instruments. Beyond the span of recorded history, rogue planets remind us that the cosmos is larger than our assumptions. Because when we first imagined planets, we pictured them only as companions to stars, points of light orbiting brighter points of light. It took deeper thinking and detailed simulations and subtle observations to realize that many planets might not orbit stars at all. Now, they have become part of our catalog of cosmic objects, alongside stars, brown dwarfs, gas clouds, and black holes. In the same way, your understanding of your own life and experience can expand over time to include things you did not originally imagine, new roles, new skills, new perspectives. What once seemed impossible or unlikely can become part of your internal map of what is real. If the evidence and reasoning support it, the universe is not static, neither is your picture of it. And yet, even as our understanding changes, there is a steady background, the constancy of physical law, the predictability of gravity and energy conservation, the slow cooling of hot things, the slow mixing of gases and fluids. Rogue planets embody that constancy. They are not dramatic, but they persist. They travel on, through the galaxy's changing environment, unaffected by the day-to-day details of life on any one world. Their journeys span hundreds of millions of years per galactic orbit. Their thermal histories extend over billions of years. Their current states reflect cumulative processes that began long before any human being existed. When you think about this, smaller worries can feel a little lighter. Not because they are unimportant to you, but because you can place them against a much larger backdrop. You can see that there is room within such a vast and patient universe for you to rest, to step back, to let your mind become quiet for a while. You do not need to solve everything tonight. The galaxy will continue its slow rotation. Rogue planets will continue to drift, stars will continue to burn, gas will continue to cool and collapse and form new systems. Whether or not you are actively thinking about them, you are allowed to pause. In this moment, you can imagine yourself floating in space, above the galactic disk, looking down at the spiral structure, knowing that somewhere within that structure is Earth, a small, bright world orbiting a modest star, and scattered throughout the disk, far from the bright main sequence of suns, are the rogue planets. From your vantage point, you see them as invisible markers, points where world-sized masses move through the dark, their presence known only through their gravitational pull, and perhaps a faint infrared glow. Their paths are smooth, curved arcs around the galactic center, interweaving, crossing, deflected slightly by chance encounters, but always constrained by the large-scale potential. There is no rush, no sharp corners, no abrupt stops, only continuous, gentle motion. As you follow these orbits with your imagination, your breathing can match that slow, measured pace. Inhale, and picture a rogue planet moving a tiny step along its orbit. Exhale, and picture billions of years of such steps, accumulating into a full revolution, into many revolutions, into a long, unbroken record of quiet persistence. You may also notice something else. In this wide cosmic view, loneliness takes on a different meaning. A rogue planet is lonely in the sense that it lacks a central star. It does not belong to a bright, obvious system of planet and sun, yet it is still part of the galaxy, still part of the gravitational network that links all masses together, still immersed in the same cosmic background, the same radiation fields, the same dark matter halo. As every other object in the Milky Way, its path is shaped by the combined pull of billions of stars, even if no single star dominates its environment. In that sense, it is alone and not alone at the same time. You too can feel separate at times, distinct, orbiting through your own experiences and thoughts. But you are also embedded in networks of connection, relationships, histories, shared physical environments. Even when you do not feel them consciously, the universe is a web of interactions, from the smallest scales of particle physics to the grandest scales of cosmic structure. Rogue planets are threads in that web, not isolated beads floating in nothing, but nodes in a larger pattern. Even if we cannot always see the full pattern clearly, as your mind becomes softer, less tightly focused, you can let that image stay with you, a galaxy filled not just with bright stars, but with silent, dark worlds, drifting patiently, obeying gravity, carrying their internal heat and chemistry through the deep interstellar night. Somewhere in that great disk is our own planet, lit by the sun, wrapped in an atmosphere, supporting oceans and continents and life, including you. Tonight, you do not need to travel anywhere or change anything. You can simply rest on your own world, knowing that elsewhere, in the same galaxy, other worlds drift in darkness, their stories unfolding on timescales far beyond this night. The cosmos is vast enough to hold all of it. Bright stars and dark planets, illuminated surfaces and hidden oceans, noisy civilizations and untouched silence. And within that vastness, it is entirely safe for you to let go, to allow your thoughts to slow, to let your body sink into whatever supports it, to allow sleep to come in its own time. The galaxy will keep turning, rogue planets will keep drifting, physics will keep doing what it has always done. You can let yourself drift, for a while, into your own quiet, starless interior, where attention softens, where dreams may rise like gentle currents in a deep ocean, where you are carried, effortlessly, by processes that have been running since long before you were born. Just as a rogue planet does not need a destination, you do not need a particular thought or conclusion right now. You can simply wander, lightly, in imagination, or let images fade entirely, resting in darkness, knowing that even in the quietest places, in space, and in your own mind, there is structure, continuity, and a kind of enduring, peaceful motion. Breathe in, breathe out. The stars are far. The rogue planets drift, the galaxy turns, and you, tonight, can sleep,